now I add some more formal definition here. So we use this ftj to denote the frequency vector at the server j at time t. But I want to say that in most part of my talk, I'll omit this t for simplicity, but just keep remind that this fj is evolving, but not a static version. Another thing I want to emphasize is that in this model, we have a two-way communication link between the coordinator and each of the cases. So this allows the coordinator to broadcast its messages to all the servers, and it allows the server to send some updates to the coordinator. However, we do not allow mutual communication between each of the two servers. Now, in this model, the goal is to estimate some statistics of the sum vector f at all times t, while minimizing the bits of communication between the coordinator and each server. So this constraint is motivated by the power and bandwidth constraints in distributed systems. So apparently, we do not have the resource to send every update in distributed stream to the coordinator. All right, so basically this is our model. And the first problem I want to introduce is the perfect LP sampling problem in this distributed model. So now a continuous perfect LP sampler is defined as an algorithm that returns an index I at all times t with probability proportional to the piece power of its frequency fi. So this is a sampling probability, and here we allow an additive distortion, which is 1 over poly n. So this is different from another notion called approximate sampler, where we allow an absolute fractional distortion to this sampling probability. So this perfect sampler is inherently more complicated than approximate sampling. So here you can consider this LP sampler as a way of sampling an index with respect to its importance in the entire frequency vector. For example, if you have p equals to 0 here, we're just doing uniform sampling inside the universe. And if we have p equals to 1 here, we're doing uniform sampling with respect to each update in the data stream. And as you increase p, we're shifting more weights to those vectors with a larger contribution. So basically means that we are sampling heavier elements. So given this perspective of importance sampling, it has various applications to big data analysis. Moreover, it serves as an important subroutine in other streaming algorithms. And more importantly, it itself is a critical problem in the streaming setting.
Okay. In the setting, is the adversary adaptive with respect to the samples?
For the first part, this is in a non-adaptive stream. So the distributed stream is fixed in advance, and yeah, it's unclear if you can achieve this in the adaptive stream, but we do achieve the robust FP estimation in the adaptive stream, which I have specified. All right. So this problem has been extensively studied in the non-distributed streaming setting. So in that setting, you only have one server, and we prioritize the space constraint instead of communicate constraint in our distributed model. But given the importance of the distributed model, it is quite surprising that there's no existing result of this perfect LP sampler with efficient communication. So in our work, we initiate the study of this problem in the distributed setting. And in general, we want to achieve a communication sublinear to the length of the distributed stream, or even better, which is linear to the size of the universe. So our work answers this question affirmatively by providing nearly tight upper and lower bounds. So for the upper bound, we obtain a perfect LP sampler, which is correct at all times t, and it only uses k plus k to the p-1 polylog bits of communication. In addition, we can obtain unbiased estimates to the sample item, which is also a constant factor approximation. And to complement our result, we prove a lower bound of omega k plus k to the p-1 bits of communication. So basically, the lower bound is nearly tied up to polylog factors. However, due to the time limitation, I cannot go into details of the techniques here, but I should say there's several really cool technical ingredients, and you're welcome to talk in person afterwards. So here, despite its critical role in the streaming setting, it also has this. It also serves as an important subroutine in achieving robust FE estimation. And moreover, many of the technique here is also shared in our other subroutine of achieving robust FE estimation. So, given the interest of time, I move to the second part of our paper, which is the robust distributed model. So first, let me introduce how you combine this distributed setting with adversarial robustness. Again, similar as many of the talks in this workshop, we're framing it as a two-player game where you have a data source which is adapted according to the estimates, and you have an algorithm which receives the input from the data source, and you want to output the correct estimate at all time. And I also stole the picture from Samsung's slides. Yeah, but here the difference is that in each round, the data source get to choose the server first and then send some element to the server. For example, in the first round, it says server 1 element B, then your algorithm need to update the frequency vector in the first server. And then let's say the primitive of our algorithm is to estimate the F1 moment, to return estimate 1. And then the data source receives this estimate in the next round. It gives another input. And here, again, to achieve robustness, we allow the future inputs to be dependent on the past inputs and the estimates. So now, based on the queries and estimates in the first round, it says server 2 element C, and your algorithm needs to update it corresponding. And it gives the next estimate. So basically, these games can go round after round, but importantly, the algorithm needs to be correct at all times. And the goal of the data source is to trick your algorithm to make it fail at some time. So I won't repeat the motivation for this robust model because it has been discussed extensively in this workshop. All right, now let me introduce the second problem we study in our paper, which is continuous FP moment estimation. So the definition here is we want to output a 1 plus epsilon estimation to the FP moment, and it needs to be correct at all times t. Here I want to mention that in our paper, we only focus on the regime of p bigger than 2. And again, the importance of this regime is that when you increase this p, you're prioritizing the elements with a larger contribution. So one might as well think this as a interpolation between the L2 norm and the L infinity norm. And as your p approaches infinity, we're identifying the maximum of this frequency vector. Yeah, now this table summarizes several SOTA results in the non-adaptive streams. So these results are still in the distributed model, but it's just that your distributed stream is fixed before your algorithm starts, so it cannot be updated after you receive some of your estimates. So now for the regime of p bigger than 1, Wuzhou Zhang in 2012 gave this upper bound communication of k to the p minus 1 over poly epsilon plus k times phi log n, and Kanan Impala Wuzhou in 2014 gives this k to the p over epsilon squared pi log n for p between 1 and 2. And recently, a stock paper this year by Huang et al. Improves the bound for this p bigger than 2 regime, and they achieve roughly k to the p minus 1 over epsilon squared. So this is a nice result because they achieve nearly tight upper bounds compared to the communication lower bound here. So basically, their algorithm is quite simple. It's based on a LP heavy hitter algorithm and then some post-processing after you find the LP heavy hitters. However, it is unclear how to achieve robustness for this LP heavy hitter algorithm because you're something inside the algorithm, you're something several important indices from all the servers. And then if your adversary knows the inner randomness of your algorithm, it can shape its like other inputs to increase the weights of the things you don't sample, and this will fail your algorithm. So given this perspective, the main research question in our paper is that whether we can construct adversarially robust algorithms that is correct at all times for FP estimation, and it does not lose any k and 1 over epsilon vectors. And again, our result is yes, we can have this algorithm in the adversarially robust distributed setting, and it only uses k to the p minus 1 over epsilon squared pi log n. So basically, this means that we achieve robustness only with additive pi log n overheads, and we are tight in both k and 1 over epsilon. Yeah, so this is the main results of our paper. And now I'll go to the technical parts. So here, please stop me at any time if you have questions about the techniques or you're confused about anything. Begin with, let's briefly recap the sketch switching framework, which is covered in Samson's first talk. So this is a really well-known framework to achieve robustness. And the main idea is that you can implement several instances simultaneously and then switch to a new sketch whenever the estimate value goes by like epsilon f. So this framework gives you robustness because when the estimate of your sketch is not revealed to the adversary, then the adversary had no idea of your inner randomness, so it basically can do nothing of your new sketch. And after you switch this sketch, we are fixing the output of the algorithm, so it doesn't change until the next epsilon f increment. So although this really nice this really nice framework gives you adversarial robustness, a crucial drawback here is it loses a 1/epsilon factor in the complexity. And to solve this problem, which we show in 2021, gives this difference estimator framework. So basically, the main idea here is that when your increment of the estimated value is only epsilon f, we don't really need to have another instance that gives the 1 plus epsilon estimation to the new value. Instead, we can just obtain a O1 approximation to this increment, where it's the difference between the new value and the previous value at the previous one. And similarly, if the increment is only 2 epsilon times f, you need to get an estimate with a little higher accuracy, but it also suffices to give full 1/2 approximation. So again, you don't need 1 plus epsilon estimation here. So now the main idea is that you can relax the 1 plus epsilon approximation to an additive error of epsilon f, and then basically you can partition this round by several blocks with different granularities that is consistent to a geometric series, which means that you can have a epsilon f, 4 epsilon f, 2 epsilon f, and epsilon f, and you estimate each segment here with corresponding accuracy. So I won't go into more details here, but the main takeaway is that this framework gives you robustness without losing anything in 1/epsilon factors. So this will only give you a pileup and no overheads. All right, so with this powerful framework, our job is to construct this gamma epsilon FP difference estimator, and it suffices to lift this difference estimator to a robust algorithm. So now let me formally define this FP difference estimator. So you have a prefix vector u, and this u is arrived in the prior distributed stream and is static at its current time t. And then you have a vector v, which is still evolving as the distributed stream goes on, and it follows the prefix vector u. And now our goal is to estimate the difference between the fp of u plus v and fp of u. So here, for this 2 parameter gamma and epsilon, we can understand this gamma as the length of the difference you want to estimate. So basically, it means that difference term here is roughly gamma times fp of u. And another parameter epsilon just means the accuracy, which is always a additive error of epsilon times fp of u. And here, we need our difference estimator to implement in efficient communication, but I'll specify it later. All right. So in the remaining part of my talk, I'll basically show you our construction of this non-trivial difference estimator, and we introduce several novel things here. So an intuitive thought of how you can estimate this difference is that we can just identify the important indices with respect to the difference and estimate its coordinate. So you can consider it as a heavy hitter, but it's just a heavy hitter according to the difference. And the natural thought is to have this sampling-based scheme, where in particular you sample an index I according to some reasonable distribution, and then we set our estimator to be the difference, the entry-wise difference, ui plus bi to the p minus ui to the p, rescaled by the sampling probability. So the nice thing about this estimator is that it is unbiased. So if we can have a small variance, we can just average across several instances, and it will give us a correct additive error. And now the question is, how do we actually choose the sampling distribution such that it gives us a small variance? Let us consider this motivating example where your prefix vector u has an n in the first entry and all ones in all other entries, and your evolving vector v has a square root n in the last entry and all ones in all other entries. So now we might as well consider p equals to 2, and the difference of the fp in total is roughly 6n. Now you look at the difference at the first entries, it is just n plus 1 squared minus n squared, which is roughly 2n. And the difference at the last entry is roughly n. So this means that the first entry and the last entry, they are all really important in the difference. So whatever distribution we choose, we really need to sample these two entries. So again, as I mentioned earlier, our LP sampler is just something that index with respect to its importance in the frequency vector. So it's really natural here to consider using the LP sampler. However, we need to be careful here because we cannot just sample LP sample from U, because we will definitely get a first entry, but you'll never get this last entry from all this n-1 entry of ones. So this means that we need to do LP sampling from both U and B. And the next question is, when shall we LP sample from U and when shall we LP sample from B? And it turns out that the answer is really simple. We just propose this mixed LP sampling scheme, which states with probably 1/2 we can LP sample from U, and with probability the other half we do LP sample from B. So it turns out that this will already gives you a variance that goes through, because we by this mixed LP sampling scheme, we locate the important indices in both U and B, so that we find every important indices with respect to the difference. All right, let me pause here for a bit. So do you have any question at this stage? Okay.
So V is not being fixed adaptively, V is also like some fix.
V is yeah, so there are two types of difference estimator in our framework, the distributed framework. So for one type it is static, for the other type is like evolving in the distributed string. But the good thing for this difference estimator here is that in this framework, you're still doing the review and split stuff. So whenever you estimate a new difference, you review the estimate to the adversary, and you just freeze the output, so you don't need to change it. So again, your inner product is hidden from the adversary. So basically, inside this difference estimator, you do not need robustness. Yeah. All right, so after we sample some index I, it remains to compute each component of this estimate. But this is quite non-trivial, because for many of the terms here, you do not have exact value, or you cannot obtain exact value within efficient communication. So for example, we need to estimate this pretty huge formula of the inverse sampling probability. But here I do not have time to cover each of the components here. So the task of my remaining talk is to deliver how we give an unbiased estimate to this piece moment of U. So this is already quite complicated, even if your U is a prefix vector, which is static, and you can query basically anything from this U, but you still want to give an unbiased estimate with efficient communication. So as stated here, we want unbiased, and we want the variance to be constant factor, and we want a roughly k to the p-1 communication. All right, how to do this? This is by this exponential scaling scheme. So now we define this vector UP as U1 to the P, U2 to the P, to UN to the P. So basically the F1 norm of this UP is just the thing we want to estimate. And then we can obtain NIID exponential variables, and then we scale each term here correspondingly with independent exponential variable. So after this construction, we can use this really nice and classical result of max stability of exponential variables. And we can prove that the maximum of this scale vector G, which is just a random variable X. So this X has exactly the same distribution as the piece moment of U over E prime, where E prime is independent of all EIs. So given this really beautiful result, we successfully reduced this problem of finding FP moment to finding the maximum indices in this scale vector G. So suppose that we have an exact value of X, then it is our hope that we can use this distribution to give a best estimator to the thing we want in the numerator. All right, so I still have a slide about how you identify the maximizer from the scale vector G, but I don't have time to cover it. So the basic idea is that you have some subroutines that maintains this small set which contains the maximum. So you basically can you can track each element in the set PL, which stands for possibly large. So here, since UI is static, we might as well just query k servers to get this UI exactly, because this does not violate our budget for communication, which is k to the p-1. And here, if you have a evolving vector v, we can use some distributed counting algorithm, for example, the one introduced by Uri, to give a good approximation. So now suppose that you have the exact value of this variable x. The next question is, how do we get this unbiased estimate to this piece moment of u? However, this does not instantly give you this desirable estimate because both the expectation and the variance of this 1 over e prime are unbounded. So this means that the expectation of this variable x is also unbounded, and apparently this is not an unbiased estimate. Unfortunately, we have another nice property of this exponential, which states that the expectation of 1 over e prime to the 1 over p is bounded for all p bigger than 1. So unfortunately, for p equals to 1, this is not bounded. So based on this observation, we apply this geometric mean estimator, which simply, as stated in its name, you just have 3 independent versions of this variable x, and you take this geometric mean. All right, now let's do some really simple math calculations. So recall that for each of the xi here, its distribution is exactly the piece moment of u over some exponential e1. So here for the first term, you have the piece moment of u over e1 to the 1/3. And the second term is piece moment of u over e2 to the 1/3. And again, the third term is piece moment of u over e3 to the 1/3. So you can observe that the numerator is just the thing we want, which is the piece moment of u. And for the denominator, we can use this property, and we show that the expectation of each 1 over ei to the 1/3 is bounded. So this means that after you scale this variable y by some constant, your estimate will be unbiased. And moreover, we have a constant factor variance. So
So you literally just take a few of them and take the geometry?
yeah. Just 3 independent versions. Yeah, I know this geometry mean estimator is like being used to estimate some p-stable random variables in prior work, but this is the first time it's used in exponentials. And I think it's quite important because the exponential scaling is really important in both LP sampler and FP estimation. So in fact, in our LP sampler, we also use this kind of exponential scaling instead of this geometry mean estimate. All right, so yeah, but we still need to compute this estimator S, but I'll just give you a really high level intuition for it. So basically you can expand each term by some variance of Taylor expansion, and you truncate it at a log n terms. So here this Q is just log n. A nice thing for this Taylor series is that if you look at this power of p, so since we have this v as an evolving vector, we don't really get exact value here, so we need to estimate this term somehow. But this p can be a fractional number, so this will give you some undesirable covariance terms, which prevents you from getting a biased estimate. But a good thing for Taylor expansion is that this power q is actually an integer. So you get rid of this covariant terms, and basically you can run like multiple independent estimations and multiply them together. So basically this is the high level idea. A brief summary of our framework. So first, we do mixed LP sampling, and this distribution gives you a way to find those important indices I with respect to the difference. And then we compute this estimator S, which is unbiased and has its really small variance. So given the guarantee of S, we can just average across like gamma over epsilon square instances, which will give you the desirable additive error. And last, by this framework, it lift our LP difference estimator to a robust FPS stage. Let me give you a brief derivation of the communication here. So recall that the communication for our LP sampler is roughly k to the p-1. And for all the other subroutines here in this estimator S, we also only need roughly k to the p-1. And like if you ignore some polylog factors. So then this total communication will be gamma over epsilon squared times k to the p-1. And after lifting by the framework, it gives you a k to the p-1 over epsilon squared. So here, let me briefly explain why you have this reduction. So recall that this gamma factor is roughly the length of your difference. And in each round, we can divide the stream by several rounds, and each round is f doubles. So basically, it means that there are roughly 1 over gamma such difference estimator with length gamma. So it's 1 over gamma times gamma over epsilon squared, which gives you the desirable 1 over epsilon squared. Yeah. A final remark of why LP sampling. So first, a sample with respect to the importance of each coordinates. So it gives you a way to identify the important indices in both U and B, which is also important in the difference. And second, the formula of the sampling probability is rather easy to estimate and maintain. So it gives way of for us to discover those new techniques to estimate each components. And third, it is run with efficient communication, which means that we can do like several instances and averaging across them. So this shows the effectiveness of our perfect LP sampler. We also saw other streaming problems, but I won't cover it here. So the main takeaway of this talk is that our robust algorithms, by a distributed version of the difference estimator framework, achieve optimal communication compared to the non-adaptive results. If you ignore some polylog factors. All right, some future directions. First direction, which is really interesting, is you consider this NP moment estimation for P between one edge. So recall that the prior work only gives k to the p-1 over poly epsilon or k to the p over epsilon squared. So none of them is tight in both k and 1 over epsilon, even in the static version. So it's quite interesting to see what is the actual bound here. And second, of course, we can consider other applications of the difference estimator framework in a distributed setting. All right, that's for the talk. Thank you for listening.